Hi guys, this is your TA. I'm here to explain Lab 2, which is designing the program counter and the register set design. So even if you have done the lab previously, I'm just here to explain what's the correct implementation of this code. So let's design a 1-bit register first. It has D, which is data, LD is load and clear signal, and clock. So when the clock signal is rising edge, we need to take that data and store it inside the register if load is also 1. But if clear is 1, then the stored data will be forgotten and the output will be turned to 0. So let's create a new project. VHDL. This is new project. Create a new folder which has lab 2. Select folder and then lab 2 empty project. I don't want to add any files. This one you have 4E, and again if you want to check what kind of FPGA we are using, you can check that in here in the first lab. Have this code, this given, so you can copy and paste that into the filter. You get that exact device, so that you never make mistake of selecting the wrong device. So first I'll design the 1-bit register, and then the 32-bit register, and then the program counter. So I'll create a new VHDL file, and I'll save file, save as, and I'll save it as 1-bit register. Alright, and then I'll copy this code. Alright, for the implementation, the easiest way is to go online and look for the register code, 1-bit register VHDL. This is the easiest way to actually figure out what's the correct code. So not the question, the answer. So entity register 1, it has load, so it seems like they are doing the same thing. So you can just copy this code and paste it here. So entity, we first declare the entity, its name is register 1. You can but for our case, the register 1, our file name is 1-bit register, so I need to change that, 1-bit register. And then there might be a problem, so bit 1 register. So you can't start the name of the entity with the number, so I'll name it as that, and I'll file save as, and I'll save it as bit 1 register. Alright, and I can delete 1-bit register file. Alright, so even if sometimes when even if you delete it from the project, it doesn't actually delete it from the workspace or the lab project. So here it still is there, so I can delete that, and even this psk file. Alright, so the architecture description of bit 1 register is begin, and then it depends on clock and clear. So if clear is 1, our output is Q is 0, and if it is rising edge of clock, then load is 1, and then you check whether the load is 1. If the load is 1, then you load the data out into the queue. So, this is simple enough, but the key part you need to remember is why clock and clear signals are inside the process. So whatever signals are inside the process bracket, that means that whatever is inside the process, this piece of code will run every time clock and clear changes. So every time clock changes, whether it goes from 0 to 1 or 1 to 0 or rising edge or falling edge, whatever it is, whenever clock signal changes, this piece of code runs. And whenever clear signal changes, this piece of code runs. It doesn't matter whether it changes from 0 to 1 or 1 to 0. For now, since we have just defined it as clear or clock, so this process is sensitive to clock and clear. So whenever these two signals change, this piece of code will run. And in this piece, it's a good practice that when you're writing a piece of code, for example, you have if statements here, remember they are checking clear and they are checking clock. So these are the only two checks you are doing. So how to determine what signals to put in here? For example, you have it empty. So I wrote this code and now I need to figure out what this process should be sensitive to. So once I know that I'm checking clear and I'm also depending on clock, the first if statements, not the insides. So the first if statements is they allow the code to run only if the clear or the clock changes. So that's why I need to make it sensitive to clock and clear. So never mind the inside if statements, whether load is 1 or not. That's the secondary if statement. The first if statements, if, else if, so it depends, it checks these two statements. No code will run if these two statements are not true, right? So there's no else. So if there's no else, then you can put these two signals which you are checking. So this is the simple one. So don't forget the import statements. We have data, load, clear, clock, and queue. So see, it gives this error top level entity is not defined. So that is why, because you have the project name as lab2, but your top level entity or the file which you want to compile, its name is bit1 register. So how does it know which file to compile? How does it know where the main entity is? You have to do it as top level entity and then compile. Meanwhile, I'll create a new waveform file, and then in here I can say grid size. Remember, the grid size should be 100 and end time 1 micro. Okay, now I can go into insert node or bus, and then node finder, and then list. So I have all of these. I can list, put it inside. Okay, and now for the clock I can do a count, which means it goes from, it counts 0101 and count every 50 nanosecond, so that every 100 nanosecond you have a clock cycle. So this way you can actually test 10 cases. So every rising clock edge, since your component depends on rising clock edge, so you can test actually 10 cases. And in one of these cases I'll force it low. Why? Because I need to test this case. Even if there is no rising edge, there should be a clear signal. A clear one should force the output to be 0. So that should work. So for that case, I'm putting 1 clock as 0. So for this part, for this part right here, I'm going to force it high, and then maybe in the middle also force it high, and data can go, I'll count the data, count every 500. So for the half of the time it is on, and for the 0, and for the half of the time it's 1. So but I think it's a good idea to have the 1 for the first half. So I should make it count, start value 1, and then yeah. So it for the first half it is 1, and then it goes to 0. So for the load I can make it also count, so that start value 0 and then count every 100. So sometimes I'm loading, sometimes I'm not. So let's, now that it is compiled, let's run functional simulation. Yes, I want to save it. So this is my, alright. So let's test all the cases. We have data is 1. So we said that we want to load that value. So it has loaded at the rising edge. So in here, as soon as we said that there should be it should be clear, it straight away went to 0. It didn't wait for the rising clock edge. Remember, this is falling clock edge, right? So it didn't wait for the next rising clock edge to actually force the output 0. So as soon as the clear went high, the output went 0. So the same, I think the rest is still working. Data is 1, clear is 0. You're not loading it, it doesn't load. So when you're loading it, the value is 0, the output is 0. Seems like it's working. All the cases are tested. Clear is 1, load is 1. All the, if clear and load is 1, what happens? So if clear and load is 1, clear is given preference. Why? Because you code it that way. Because first if clear is checked and then the rising clock edge is tested. So clear is always given preference. If this is true, it will straight away go there and then come out of this if statement. It won't check for the rising clock edge, which is good. It's fine. So now that we have the first 1-bit register working, we can go on to make the 32-bit register. So what I'm going to do is create a new file, and I'll copy the same code in here, except that I'll name it bit 32 register, and I'll save it by the same name as the entity. Okay, so the only difference in the 32-bit register and the normal register is that these are actually STD logic vector, and this is down 31 down to 0. So the data is STD logic vector. One other thing is STD logic vector, which is the output. The rest is 1-bit, so that is fine. So the others, now this is working fine. So you have Q. Remember, now Q is not 1-bit, so you cannot force it 0 like that. So you will have to do it this way. So in X means hexadecimal, the next number which is coming is in hex. So if you type in 8 zeros, that means 32 bits. So that is the case. If clear is 1, if make the output 0. If load is 1, make the output same as data. So that is 32-bit register. Let's compile it. Alright, so it seems like it works fine. Now I can create a new waveform file for this one, and same things. Oh wait, before compiling I have to make this as top level entity and then compile it, and then I have to make file new waveform file, and then grid size should be 100, end time is 1 micro, that's fine. Insert node, let's see if it finds it before the compilation. Yeah, finds it, so you can add in all of them. Alright, okay, So these numbers are very difficult to read in binary, so you can convert them to hexadecimal so that they are easy to understand. So same with the clock, I can click on clock and make it count every 50 nanosecond. So every 100 nanosecond is my clock cycle. And then clear, so I'll have two clear statements. One is here, value force high, one here, because half of the time I'll keep the data as something else and half of the time I'll keep it something else. So okay, no, not like that. You can do count and then let me do A, D, F, 1, some random number. So I'll increment by 6, count every 550, no, 100. So we can count every 100. Now also remember that one of the cases we need to make the value to go 0, all of them, and one another case we need to make the value all high. So FFF, this is the most usual case, you have to test these cases. Then I'll make this one also count, and I'll make this count every 200. It's more probable that your load 1 is wrong, so I'll make more load 1. So less cases are for load equals to 0. So is there any case where load and clear are 1? Yes. So there are two cases. So let's see what happens. If load is not 1 and clear is 1, what happens then? So you can select this one here and then value force high. Alright, so let me not do that. In here I'll force it high, and here. So this part you have to actually think yourself that what are the possible combinations I can test. What you can test your entity to limits, that where. So why I'm making clear here 1, because it will load the value, and by the time it reaches here I want to see what happens to that loaded value. If it was always 0, I won't know what it is actually doing. I hope you understand that. So what's the name of the entity? Bit 32 register. Alright, so load is 1 and rising clock edge, it load is 0. Clear is 1 and load is 1, so it did not look at load, it looked at clear, because you have the if statement of clear first. That is correct behavior. And then the rising edge, it loaded that value. What happens if load is 0 and clear is 1? It clears, but see this behavior. When the signal of clear is 1, it doesn't wait for the next clock cycle. It didn't change here, it changed here in this moment. When there was, as soon as the clear signal went up, it changed. So if I change the code, if I go back to the code and if I remove this, now that won't happen, because it will actually look for change in clock and then figure out whether the clear should be 1. So that is wrong implementation. So the clear should not wait for the clock to happen. Once you want to clear something, it should happen instantaneously. It shouldn't wait for the clock cycle to occur. Now the rising, this is load, and then clear, same situation as that one, so it should clear, and then you are loading FFF, that loads correctly, and then you are loading this value, it loads correctly, and then you're not loading. Yeah, so most of the cases are tested here. Now let's move on to the 1-bit register. Not 1-bit register, the PC program counter, right? So the program counter just has one more signal, which is increment. So if I go back to my project and create a new VHDL file, and I'll copy and paste this code here and save it as PC, right? And I'll name it as PC. Same. Now here the difference is that I have one more statement, one more signal, which is increment. Now most of you actually made this mistake that when the PC is supposed to increment, the load also has to be 1. So okay, let me explain that on the okay. So you have PC over here. So this is your PC, and then this PC actually is connected to your instruction memory. So this PC actually provides the address of the next instruction memory to load. So instruction memory is like a shelf, and it has many places to store, and then each of that actually has an address. So the first one is 0000000. Second one is 000000001. Same until if it is 256, it will go up to 11111111. So these are addresses, and in each places, it's like post box of the Canada Post. Each box can have any content, and each box has a address or box number. So the address is actually the box number, and whatever is inside, you can store letters, you can store anything. So in here, inside the instructions, you have instructions. Instruction memory, you have instructions, and each instruction actually has the address. But the problem with the memory is that each memory location only stores 8 bits. So there's only 8 bits in one location. So we are designing a CPU. We are designing a CPU which takes in 8-bit 32-bit instructions. So this CPU takes in 32-bit instruction. How can we actually take instructions from here and load it into the CPU? Our one address actually stores 8 bits. So the answer is that you need 4 of these locations: 002, 01, 02, 03, up to 03. So 4 of them actually stores one instruction. Why? Because at each location you have 8 bits. So whenever PC gives the address, it actually gives the next address plus 4. For example, now what your instruction you are executing is from 000 to 004. So the next address for the next instruction will be from here to there, right? So it will start from 0004 to 00008. 7, not 8. So 4 to 7, that's 4 memory locations. So each time PC needs to give another number or generate another number. For example, the previously CPU was executing instruction 000. It needs to jump over to 004. It then from 004 it needs to jump into 008. So that's why when the increment signal for the PC, there is an increment signal. Whenever increment signal is 1, it needs to take the number it has previously stored in and add 4 to it, and then give the that's the next instruction's address. So instructions are stored in sequence in this array fashion in the memory. So each instruction is 32-bit. That's why we need to increment by 4. So but the problem is, you guys assume that whenever increment signal is 1, load also has to be 1. Why load has to be 1 in order to increment? No, that's not the case. When load can be 0, load is used to jump or tell the PC that now I want to execute a specific instruction from specific location. For example, let's say that my first instruction is stored in 0009, right? So I will say load equals to 1, and then I will give it data, which is 0009. So I will, when I say load equals to 1 and data equals to 009, I am saying that my first instruction is stored in that location, start counting from that location. All right, so once I have set that, I can remove data signal, I can remove load signal, and at next clock cycle, when I have taken that instruction from that location and executed it, the next instruction should be at 0009 plus 4, that should be at 13, right? 13 is C. Okay, it's D. So 13 is D. So when, then that's the next instruction. So I don't have to load that value again into the data and then into the PC. Otherwise, what's the use of the PC if I have to load the increment the value and then load it again? No, I have done that part. So I will just say increment equals to 1. It knows what previous value was. Previous value was 009. It will generate the next number and give the address to the instruction memory. Instruction memory will grab that instruction and pass it to the CPU. So this is what we are designing here. So we have increment signal. If clear is 1, Q is 0, else if rising edge, and then clock. And then inside here, when it's critical that the rising edge event happens, and then only you check for the increment signal. So in here, I'll say if increment equals to 1, then Q equals to D plus 4. One more thing about this is that you can't do D plus 4 because D, it remembers the previous value of D. If you want to increment twice, so what you incremented once, it made 009 to 00D. If you increment it again, it will take the same old 009 and increment again for to that number and then give you the output. That's why we need to use Q. We will assign Q plus 4, not D plus 4. That's why when we use the output as the input again, we need to say Q is also as input and output. So you need to make that change there, and you need to add this if statement. Remember where I placed the increment signal, it's not inside the load. What you guys did was, some of you guys are putting the signal inside here, and then you have a else statement there. No, that's wrong. Why the load has to be 1 in order to increment? This is a separate statement, this is separate if statement. Both of these statements depend on the rising clock edge. Your Q signal has to be input and output. Let's see if this compiles or not. Also keep in mind, you need to add these two statements, otherwise this plus won't work. So if you compile now, after adding those two import statements, in 32-bit register you don't need the arithmetic operations. In this one you need the arithmetic operation because you're doing a plus. So you take the Q signal and then add 4 to it. That's why the import statements are different for PC, and then 32-bit register only has 2 imports. So same with this one, I can go and create a new waveform file, and then same rules apply here. I can say grid size should be 100 and time is correct. You can find all the nodes. Okay, so this is the, so what happened was I did not make it as top level entity, and then I have to hit compile, file new, university program. Make sure your grid size is 100. Alright, now it appears because I had to make it top level entity. So I can convert it to hexadecimal. Again, same rules apply here with the 32-bit. Whatever I did with 32-bit register, same rules apply here. So clock will go 50 nanoseconds so that I have a clock period in 100. Clear, I'll make it clear sometimes. Now I can do count for the data. I can do increment by 8. Count every, not the same as clock cycle, you have to do it 100. And then increment, I'll increment it for 2 consecutive times, and then here maybe force high, and then here again. No, I'll leave it there. So at random locations, 2 consecutive ones and then 1 1. I need to look at 2 consecutive because I load the value here and then increment by 1 and then again increment by 1. How does it work? So I'll make load 1 here so that it loads at that moment, and then I'll just increment them. Then I'll load another value. Oh, I have a clear one there. So I'll load another value and then clear it, and then here I can make it 0 again. So here again we have clear, and I want to test a case where increment, load and clear is 1 at the same time. So this is one statement, 0 1 0 1 0 0. So almost all the cases are there. Now we can run this as functional and see how it performs. So now I'll run the functional simulation for this one and see how the results are. Okay, so I loaded the value here, turns out it's fine. I loaded the value there and then incremented it, so it did increment once and then twice, so it is incrementing correctly. Then loaded the new value, and then as soon as clear went up, it cleared, and then here it stays clear because there's no input, no control. Then increment is 1, so it remembers 0 0 and increments by 1 at rising clock edge. If all of them are 1, it takes preference, clear takes preference, because that if statement is before everyone. So that is working fine. So you are done with this lab when you have this simulation. So in this lab, to recap, we designed 1-bit register, a 32-bit register, and a program counter. A program counter is just a glorified 32-bit register which just has one more signal, which is increment. It was so easy to implement it if you knew exactly what kind of behavior you wanted. This increment signal was not supposed to be inside the load. Some of you guys even did this, load and then you said increment equals to 1. So that is also wrong, and anybody who has that or has increment signal inside the load, that is also wrong. That is not the desired behavior of the program counter. Whenever some lab is given to you and we say that we are going to use program counter, we are going to use 1-bit register or 32-bit register, it's your duty to actually go online and look at it, what program counter actually is. So you can look at program counter, what exactly does it do, and maybe you can find online codes also that can help you guide in the right direction. So here you can see what the program counter actually does, and also in your theory, in your lecture notes, this is also discussed when you discuss the CPU, how CPU is created. That's all, folks. Thank you.